An AI can sound perfectly confident, even human, and be completely wrong. This isn't just a technical glitch, it's a fundamental paradox. The better a model gets at sounding plausible, the harder it becomes to trust its answers. So why do these systems feel so intelligent, yet fail so profoundly?
This gets to the heart of what's called the AI trust paradox. It's this growing gap between what sounds correct and what is actually accurate. The model's own proficiency with language can mask its underlying errors, which makes those errors much harder to detect and often far more impactful when they're discovered.
This raises a crucial question. How can a system be so capable one moment and so fundamentally wrong the next? The answer isn't a simple bug. In many cases, this is an intentional outcome of how these models are trained. To understand why, we have to look at their initial learning process.
Often, the root cause of these failures is established long before the AI is ever used in the real world. The plausibility problem begins during the model's training. This is a key distinction. The issue isn't always a flaw in the system's code. Sometimes, the failure is actually a feature of how the model was taught to think. These plausible-sounding errors aren't random accidents. They are the logical output of a flawed learning process.
This brings us to a core flaw in that foundation: the difference between learning and simply memorizing. One of the most common training errors creates a system that appears intelligent but is actually quite brittle.
The technical term for this is overfitting. Essentially, the model learns its training data too well. It's like a student who memorizes the exact answers for a practice test, including any typos, instead of learning the underlying concepts. The model learns the noise and random details in the data, not the general pattern it's supposed to.
The result is a model that performs brilliantly on data it has already seen, but fails when it encounters new, real-world situations. It can't generalize its knowledge. This makes it unreliable in practice. But this kind of training flaw is only one source of the problem.
Even a perfectly trained model can fail. The issue is that the world it operates in changes, but the model itself doesn't. Its knowledge, which was once accurate, becomes an outdated map. This phenomenon is called concept drift. It happens when the statistical properties of the world shift, making the model's learned patterns obsolete. Think of it like trying to navigate a modern city using a map from 10 years ago. The core layout might be the same, but new roads and changing traffic patterns make the old map dangerously unreliable. So, let's contrast these two issues. Overfitting happens during training. It's a problem with the model's initial creation. It learns the noise instead of the signal. Concept drift happens after deployment, as the world changes. The signal the model learned is no longer relevant. One is a flaw in how the model was built. The other is a failure to maintain it.
When these hidden issues go unaddressed, they can lead to more than just minor errors. Small drifts and unseen flaws can compound over time, leading to unpredictable, high-impact failures.
These types of failures share characteristics with what are known as black swan events. First, the event is a surprise. It falls outside normal expectations. Second, it has an extreme impact. And third, in hindsight, it seems explainable and predictable.
And there are documented cases where AI model failures led to severe consequences. In healthcare, a system reportedly gave unsafe treatment recommendations. In real estate, a flawed pricing algorithm led to hundreds of millions in losses. And in transportation, an autonomous vehicle's failure to react resulted in a fatality.
Now, while these specific examples may not meet the strict definition of a black swan, they do demonstrate a similar dynamic: how hidden, internal model issues can produce high-impact, unexpected outcomes in the real world. This leads to the central challenge of reliability. If these problems are inherent to how AI is built and deployed, what is the framework for building systems that can actually be trusted? There isn't a single technical fix. Instead, reliability requires a disciplined approach across several areas. It starts with addressing data issues by ensuring high-quality, representative data. To counter model drift, it requires continuous monitoring. For complex models, rigorous testing is essential. And finally, to ensure accountability, a strong governance framework must be in place. The critical point is that reliability is not a one-time fix. It's a continuous cycle. The system must be constantly monitored, tested, and adapted to stay aligned with the changing world. It's an ongoing process, not a final state.
This leaves us with a fundamental, forward-looking question. As these systems become more integrated into critical functions, we must confront the central challenge. How do we build durable trust in systems that are designed to operate in a world that never stops changing?